Okay, so somebody pointed out that actually, not only do I start 2 or 3 minutes late, but I go over 10 minutes too far. I shouldn't be ending at 12:45, but 12:35, which means I have to increase my speed about 3%. Okay? So last time we talked about Q-learning, and I mentioned 2 ways of approximating, 2 algorithms. And you've got this to your notes. Don't be secretaries. Just I need this in front of me for a second. There you have it. So the first was this approximate dynamic programming algorithm, which, I mean, this would just be something you'd do in a simulator. And it's not really approximate because we're trying to compute this exactly. You know, it's just, that's how we would call it, because we're not looking at a real physical system, looking at input-output measurements. We're generating this based on a model. And I'll let you go back and look, what this was. This would be distributed according to x of n plus 1 if, see your notes. So, if at time n, x of t was x and u of t was u, then the next state would be distributed according to this random variable. But look at your notes. I don't want to review the whole lecture. So in order to generate this random variable, you have to have the model. Now, the original Q-learning algorithm was reinforcement learning. There you have it. You basically, the new estimate of Q star was equal to the old estimate of old x star for all x and u except for 1. So last time I gave this a distinguished name, I called it x0, u0, just trying to say it was special, and a lot of you are confused by that. So I just go, at time n, there's I observe one particular value of x of n, one particular value of u of n. This is a reality, right? I'm looking at an input-output system, and there's going to be one particular u and x that I observe. And for that, what I observe, I then make a change for the next step. And everything's the same. Okay, so then this is n plus 1. Yep. So for the particular xu that I observe at time n, if I'm patient, wait one more time step, I will observe the next value, xn plus 1, and I update that particular pair xu. Okay? So you can imagine for a large state space and with a lot of inputs, you might wait hours and hours and hours to get to update one entry of the Q function. So that's why it's really slow. And so that's why it's easy to laugh at it. So what we'd really like to do is not try to compute this, but approximate it. What we'd really like is that. What's needed is approximation techniques. So it's like a parameter in some d-dimensional space where d is much less than the number of states times the number of actions. I mean, That's what the Q function is. The Q function is a big vector, and its dimension is the number of states times the number of inputs. That's crazy. And what we'd like to do is come up with a permutation. Now that's not in the literature. I mean, so I have one paper with Prashant Mehta for the deterministic case, which is a really nice algorithm. That's the only one I know of. I mean, so you can find my own work. And there's a paper by Betsikis and Yu, I think it's 2008. It's only for stopping, optimal stopping. So basically, I'm observing a Markov chain, and I want to know the optimal time to stop, like the gambling problem. When do I walk away from the casino? You know, so there's no control besides stopping. So that's the state of the art right now. There's nothing else. There's all sorts of ad hoc, crappy algorithms out there, but there's no convergence guarantees. There's nothing. There's no theory at all. I can give you 1,000 references, but and the problem is just the fact that if I come with a parameter, I might have a linear parameterization. When I take a minimum, I get something concave, and that causes issues. I think there's a fix. You know, I think that we'll have this solved within a year. But, there'll be some nice algorithms. And, I have all sorts of ideas of how to do this, but the best way is still a frontier. In terms of analysis, one second. Here. In terms of analysis, if Q, so notice I don't have a star here, so Q is an approximation. So let's give this a name. So this error, we want this to be 0. It's not 0 if you've got an approximation. Give us a name and call that the Bellman error. Well, my claim is Q is optimal. You just have to change the cost function. So can you all see that if I take that error, I just define this to be the Bellman error, right? If I take this and I multiply both sides, add minus it to both sides, I'll get 0, right? Epsilon minus epsilon is 0. But what's minus c minus epsilon? It's a new cost function. So for any q you give me, it's a q function. Right?
Shouldn't we be making some assumptions about the boundedness of epsilon?
Well, let's say, I mean, so it might be a really lousy cost function. So if you had a general state space, my original cost was nice and quadratic. This new cost might be a quadratic going downward. Not a very nice cost function. So but it's a way of thinking. So you go through and you start out with a cost function which was quadratic, and you find out, Jesus, now instead of x squared, it's x squared plus x to the 3/2. You think to yourself, well, that's perfectly good. In fact, that might be a better cost function than So in a way, you can say, well, God, my cost function was pretty arbitrary to begin with, And so often you can just say, hey, problem solved. We'll just change my objective. So it's a cool way of analyzing this. Basically, you want to define your approximation so that you're optimized with the expected cost function that you think is useful. You know? It's a weird way of thinking about the problem. This is also called inverse dynamic programming. Normally in dynamic programming, you're given the cost, you want to find a value function. Here, I give you a value function, I find the cost.
Is it the Q minus estimation?
So this is a Q function that solves the DP equation. I'm saying, suppose somebody gave me an approximation, maybe through some algorithm like this. How do I evaluate it? And I'm saying the way to evaluate it is the way that's typically done in the literature is you look at this Bellman error, and this interpretation is really valuable. Basically, it does solve a DP equation with a modified cost. And so what you really want is you want this to be typically much smaller than this, you know, when you solve it. Clear? All right. So, all right. So I sort of want to stop there because I
Excuse
mean,
me?
yeah.
It should be a minus beta pu
Oh, did I make a minus there?
in the Bellman error.
Minus C minus
Cost negative.
Combined.
Oh, I see. I see. Thank you. All right. So yeah, I mean, so you know, how you can get away with things in the deterministic case, or the, well, you know, it's beyond the scope of this course. But there's some papers if you're interested. I can send you. Okay. Fill this. So where approximations like this are really simple is TD learning. Okay. Now the first, and this is Bartow and Sutton, I forgot. Late 80s, I've forgotten the exact year. I'll get back to you. Basically, they're looking at, again, let's stick to the discounted cost. It makes it easier to explain things. And a fixed policy. So we're not looking at optimization now, we're just trying to find a dynamic program, I mean a value function for a fixed policy. Okay. Now, why have I suddenly dropped the U? It's a fixed policy. It's just a Markov chain. No. Fixed, I should say fixed stationary policy. Okay. So basically, once you've closed the loop, it's a fixed policy. It's just a Markov chain. And the cost was a function of x and u, but u is a function of x. So it's just, you know, forget it. So it's basically you've got a Markov chain, and you want to try to estimate this kind of value function. Now, they have a, I'm going to keep things general to begin with. You know, just to be fair to the community, I mean, they definitely just looked at a completely general family of parameterizations. So theta is some parameter. Is a family of functions parametered by theta. I'm going to assume it's smooth. You know, I'm going to assume that the gradient with respect to theta I won't say what I mean by nice, but you know, it's going to be continuous, say, in theta, things like that. It's going to be well-behaved. A derivative exists. And this is just the notation I'm going to use. Okay. And they didn't look at the Bellman error, which we could look at. They looked at the actual mean square error. Now, again, I keep saying over and over again, functions are column vectors, functions are column vectors, functions are column vectors, functions are column vectors. So it's an L2 norm. But if you take any old L2 norm, you won't get anything. It's only one L2 norm. Well, that's not true. There's one L2 norm they looked at. It's been extended a tiny bit. But if you don't choose the right norm, you don't get an algorithm. So I'll put a little pi there. Okay, so this is an ergodic norm, if you like. It's the expectation of the error, the mean square error in steady state. And if given the fact that we're looking for simulation-based algorithms, it's natural that we look at steady-state means. But that's not the reason. The reason that you look at steady-state means is because it makes the algorithm work. Because after all, this is fishy. I'm trying to get this approximation. You can all imagine, I'm going to take derivatives and set them equal to 0. And you can all see my solution is going to depend on h. I don't know h. There's something fishy going on. And the only way to be able to make it so I can get something computable is by looking at steady state, as we will see. Because I'm speeding up my speaking speed by about 3%, as you can see. All right, so we do it. Take gradients. So what I'd like to do now is I want to take the gradient of this objective function set equal to 0 to minimize this mean square error. And of course, there's some hope here that I can then take the gradient inside the expectation. And that's why I need this to be nice. I'll need some bounds and all that, which I don't have time. It would take an hour to go through that. I would need the mean value theorem. I'd have to be really clear about what I need there. But I will give you some conditions in a simplified setting later on. But let's just assume we can take the derivative inside the expectation. And we all know how to differentiate this, right? The derivative square, it's twice what's inside times the derivative of what's inside. And we just define the derivative of this with respect to theta is phi. Done. Okay, so this is a vector. That's a scalar. That's a vector, which is an RD. And so this 0 is a vector in RD. And that's it. So there's an expression for the optimal theta. The theta which minimizes the mean square error will be a solution to this equation. And as you see, it depends on h, which is a real issue. So let's fix that. This is the fun part. So this is the real. They must have just been screaming when they came up with this. And I could just hear it. So how did they deal with this issue? So that's a thing. This took nerve. You look at this objective function, and right away you would stop yourself and say, "It's ridiculous. Why would I look at an objective function I know I can't solve? Because when I solve this, I know it's involving h. So why even bother?" But so it takes some courage, to just play around. All right. And so that's what they did. They played around. Okay, so I can kill this. So here's the problem we're faced with. I mean, basically, this is a bunch of functions lined up together to form a column vector, and I want to understand how I could possibly estimate this, given the fact that I don't know h. How could you do it? And there's a beautiful trick. So let's just go back and remember what these things are. Well, and I want to keep this. I somehow have to keep this. Okay, so let's see, we're countable state space, finite state space. You can all agree that that question mark is this. It's all in steady state. This is a pi here, if you like. This means if I leave that out, but everything's in steady state. So that's the definition. But what's h? H of x was just this. All right? Yep. Definition. Now I can shovel things around. G of x can go inside. And I can play around a bit. All right? I can, G of x is just G of x of 0. Stick it back in. Somebody wake up. I did two things here. I said G of x can go, be slipped in here. It's just a constant. G of x, it's a number. It's 26. I don't know. But x of 0 is x. X of 0 is x. And I was summing over x, pi of x. Well, that's just the expectation, pi. Nothing done here but a bit of algebra. Nothing. Interpretation. Now, so nothing at all. Now it's the ingenious step. What's the ingenious step? Well, before I get to it, I mean, just think about the issue here. I said, I'm trying to estimate h, which was this, which is something about the future. I mean, it's predictions about the mean of the cost way in the future, which I've never observed yet. Wouldn't it be nice if I could take something estimated in the past? There's a hint for you. I've observed the past. So the estimation is easy. So I'd like to go to the past instead of the future. And so now what I want to do is use stationary. This is why stationary of xt is critical. So let's assume that x, the stationary process, is defined for all time, negative and infinite. And if you don't know what stationary means, don't worry about it. I just mean that in this particular case, what I really care about is xt has distribution pi for every time, including t equals minus a billion, minus a trillion, minus the infinity plus infinity. So if you don't know this language, you need to take stochastic processes. Okay? You really need to. But stationarity means I can subtract time. And if I have it, that's fine. I like that. So all I've done is I've subtracted t from both of these indices. I've shifted time. Stationary means if I shift time, I don't change the statistics. So it's the exact same thing. All right? And I don't like that, though. This I like. This is getting closer to something that I like. Does this start to look like something you might have seen in singleton systems?
Convolution.
Yeah. First of all, it's like a convolution with that beta of t, though. And why am I erasing this? I was doing such a good job. Anyway, it's okay. But you can think of it as a convolution, but you can also think of it as something else. What would that mean? If I'm writing this, what would that be? If somebody's taking signals and systems, what's G beta n? It must be the sum of beta to t times. I'm just passing G through a low-pass filter. This sum this convolution between beta and G, is passing G through a low-pass filter, and it can be written in this recursive form. Yeah. And so it's right out of signals and systems. So Bartow and Sutton had never taken signals and systems, but that's what they were doing. And so what they've done now is they've actually taken something non-causal, something that you're trying to estimate which is in the future, and they've replaced it by something involving expectation of the cost, which you observe at time n, and something that you're going to pass through a low-pass filter. Yeah, that's it. So unfortunately, like an idiot, I erased my equation, but let's stick it back in. So let's plug this into 0 equals the expectation of h of x minus h theta of x times psi theta of x. And don't yell at me. I know I switch these around, but if I multiply by minus sign, I don't change the sign. And so that product was the thing that was scaring me, but now we know how to deal with it. So we've got TD learning. So what I want to do is I want to use this equation to be able to come with an algorithm for you. And so can I kill this derivation? Questions? Just the critical thing was the stationarity here.
Psi theta is a vector, right?
And size a vector, yeah. So what? Each entry is going to be subtracted. Doesn't matter. I'll do it element by element. You know, saying that this is 0. All right. If you're going to be.
Okay. No,
It doesn't matter. It doesn't matter. See, that's the ith component of psi is a scalar value function. All right. So let's go do it then. Okay, so here's version 0 of TD learning, which Bartow and Sutton came up with, and it crashed. But I'll give it to you anyway. So we want this to be 0. So we all know what to do with stochastic approximation. Now, they didn't know about stochastic approximation, so it took more genius. I mean, they didn't have that background, you know. So the fact that they came with this algorithm is pretty impressive. They had no idea what stochastic approximation was. But we know we've got this thing here. Write it down. We all know that what you do in stochastic approximation, if you want something to be 0, you take that, plug it in. Except I wish that I think I jumped a step. Let's do it as a joke, okay? This is not what anyone would do. Nobody would do this. But if you were just given this and you said stochastic approximation, you'd rip off the expectation signs, slap it in, multiply by a gain, put in your right bracket to avoid a error in MATLAB, and run it. Okay? And you'd find that you didn't have access to H, so you'd be dead. But you can go through and rewrite this. So I've got my H times psi. I'm going to have to write that as C times a filtered version of psi. Just for you, I'll put in the thing there. This is an argue. So basically, I'm just doing pattern recognition. I have this expectation of H times any function G. I've got an H times psi, and I've run out of places to put beta, so I'll just call this psi sub n theta. So it's the low-pass filtered version of psi. Okay. So let's cross this out. It can't be implemented. This can't run because we don't have access to H, so instead we run this. Okay, now let's be careful. So I've got to put in this and then define it. Okay, so this is the step one. This is a step one of the original TD learning algorithm, is to just apply this sort of stochastic approximation recursion. And then you've got to define what I mean by this, and again, it's low pass filter. And there it is. That's the same low-pass filter description I gave you before. And that's it, isn't it? These vectors they call the eligibility vectors. Now, somebody gave me a beautiful answer for why the Q function was a quality function. Why are these eligible? You know, I don't know. All right, so why do I call this, that's true, that's it. So that's a complete algorithm. Why do I call it V1? Because it didn't work. In theory it converges, but the variance is so huge in most examples, it just blows up. And it takes 100 million samples to converge. So V lambda is TV lambda. And the idea is to reduce the variance by introducing bias. You know? So how can I give you a 0 variance estimate of the stock market tomorrow? That's an example. 0 variance. You know? My variance of my sample panels will be 0. Every day, my estimate of tomorrow will be 0. You know? I will always say, tomorrow the world ends. Every day. So the variance of my predictions is 0. That's what they do. So what you do is you introduce something to smooth out your results, but introduce a lot of bias. And so I just forget it. I don't know why this keeps persisting. I mean, forget it. I mean, if somebody can find to us, their advisors, why this still persists, I just don't get it. You know, we've got 10 minutes. Let's do this right. You know? So this is ridiculous. I really do. I don't know why it persists. There's much better ways to go. So the reason this high variance, I mean, I have a feeling that I might give it some nighttime lectures to explain it. That's something else. But let me go and let's look at something better. So I mean, you know, so I'm sure there are lots of examples of this algorithm will work really well in applications. But in many applications, which you'll find, while this converges, it takes 100 million samples to converge. And so something has to be done to improve the speed of convergence. And to reduce variance, there's weighted norms. Which I'm not going to get into. I don't have time. And there's something called least squares sample difference learning. So least squares sample difference learning. And if you know something about stochastic approximation, then wham, that's what of course you should do. If you see high variance, then you shouldn't use steepest descent. You should use something approximating different routes. And that's what I can't stand the courses ending, because I really would like to be able to spend some time on that. But I'll explain this, I'll explain LSTD just in one setting, and maybe start today and then end it on next lecture. Now, it's not necessary. I could define a Newton-Raphson type algorithm even for a nonlinear parameterization, but things are really elegant if you take a linear parameterization. And let's destroy all this beautiful work that we've done. first thing I want to just point out is that this notation is consistent. The gradient of this with respect to theta is just psi of x, which now doesn't depend on theta. So when you have a linear parameterization, right away the algorithm simplifies because these psi's don't depend on theta. All right? So the TD learning itself will be simplified. The variance issues are still there. The variance issues are there. So then, in this case, if this is a linear parameterization, look at the mean square error when you've got a linear function. It's least squares. It's a projection theorem, And we can go through and we can just nail this. And I wish that, if you all had a functional analysis course, you'd say, oh my God, projection theorem, inner products, wham, wham, wham. Just be so. Take functional analysis, stochastic processes, and then functional analysis. But anyway, we've got the equations. We said that. We take the derivative. You kill this now. Why don't we call it a theta? It's a 0. So 0 is equal to this we saw before. But now that's just linear, and that's linear there too. And this we said was equal to the expectation of what? Of C of x times what I'll call it psi beta now. I'll use that notation. Actually, I'll define psi beta is where you pass psi through the low pass filter. So x was just a stationary version of the Markov chain. So particularly I could take xn in my previous notation. And so what I called psi beta was this low pass version of psi. Examples before. And do you see why I'm doing this shuffling around here? So I said that the expectation of this product I've already said is equal to that. Now why would I do all this shuffling around here? Well, it's because that's a matrix times theta. That's just some vector. That's a matrix times theta. Okay, so the matrix M is just this. It's just the matrix multiplying theta. And B is just this. And now, again, we're out of time, but we can throw stochastic approximation out the window. I mean, do you all know how you would estimate this? Look at the, I don't know, just, we had a few lectures on Monte Carlo simulation. We know how to estimate means. So you can take sample path averages to estimate this. We've done that. How would you estimate this? Well, the same thing. I mean, basically, this is just taking the process, passing through a low-pass filter. So, you know, so I mean, I only have 1 minute, so I don't want to write the algorithm, but we'll write it down next lecture. But, so it's a least squares problem, and it has a simple solution. The genius was that one step, is going from something non-causal to something causal. That was really the brilliance of this algorithm. And least squares temporal difference learning is just beautiful. It does not have this variance problem. And so I don't know why people use that fix, that lambda fix, which creates bias to reduce the variance. All right, so we're out of time. Sorry for holding you up the last 40 lectures. There's an exam again tomorrow evening. And I sent an email out this morning. I found out I have a personal issue. I have to leave at 5. So is 3:30 till 5 p.m. okay for office hours? I hope so. If anybody has a real crisis, tell me and I'll try to do something. I don't know what to do today. I've got an emergency myself right now for the next half hour or so. But anyway, contact me. Just let me know after lecture right now. It doesn't issue for me. Okay?